Should I start?
Yes, please.
Awesome. Thank you. Thank you for the invitation. Yes, I want to talk about a few principles that we are working in my lab that we believe are quite generic actually to develop autonomous mobility, autonomous platforms, navigation, and let me dive into it by motivating first mobility. And there is this documentary on Netflix that describes life on Earth as quite dependent on mobility. So the concept of life depends on the freedom to move. At any given moment, billions of humans are moving to eat, work, discover, connect. But then the question that we ask ourselves, is it safe, sustainable, and even accessible to all? We know that every year, 1 million of humans die in car accidents due to human errors. These car accidents cost 800 billion per year in the US, and 500,000 of people suffer from spinal cord injuries per year. Can we address all these challenges? Let's look at this road. Some kids came out of the bus and decided to cross the street. What saved the kid is autonomy. AI, and more specifically computer vision, is used to detect objects in real time and control the truck to avoid the collision. Our goal is to bring a safe yet effective mobility for all by advancing autonomy, fostering autonomous mobility. And it's not only for self-driving cars, it's for self-driving trains, self-driving ships, boats, drones, scooters, anything that moves, and even human at the end. Then the question is, do we have the AI to develop autonomous mobility? I'm going to use the autonomous driving as an example. So if we look at the AI of a self-driving car, the first step is perception, detection, detecting everything around the vehicle. And nowadays, this is quite impressive, and we do have working solutions. We do have algorithms that are quite good in detecting all the objects of interest. And then the next step is planning a path accordingly. But then we still have accidents. Well, we still don't have self-driving car operating usually at scale around us. And one reason we believe is the lack of being able to anticipate the future. So when we look at this pedestrian on the right, the AI actually fails to predict what the pedestrian will do in the next second. The pedestrian is static, but it turns out that the pedestrian decided to cross the street to catch the bus. We humans have this capability to predict this, and we believe that we need to develop modules, algorithms that can do a better job in predicting, anticipating the future of all our dynamic agents. So we should introduce another pillar, which is this prediction pillar, this social forecasting pillar. And if we want to better predict the world, we need to maybe rethink how we see what we detect. So if we only detect bounding box or just dots, points, we will not be able to do a good job in necessarily predicting the future of some of these dynamic agents. For instance, in this case, we need to maybe extract the skeleton of these humans, the focus of attention, the eye contact, the orientation, the pose, what kind of action, to be able to better predict and anticipate the future. Let me look at another type of autonomous system for autonomous navigation, a robot navigating this type of crowd. And we can use exactly the same pillars. The first one is detection. We detect everything, and then we try to plan a path according to what we have detected. But again, here, we need to develop this capability to understand that even if there are some physical paths that are physically possible, they are not socially accepted. It's not okay to go between two people talking to each other, and we need to anticipate the behavior of the person on the left to not cross path. So there is only one path that is physically and socially accepted, is the one on the right. And this is what our prediction, social forecasting pillar can tell us. And by combining all these pillars, it paves the way to, as Benjamin said, a new type of AI that we refer to as socially aware AI. And we have worked over all these pillars, and our motivation to disentangle all these steps and not do end-to-end navigation, like from an image to the control, is to actually be able to exploit all these pillars across different platforms. So whatever we develop to do detection, perception can be used on a car, but also on a robot, also on a boat or on a drone, and the same thing for prediction and planning. And the way we think about all these pillars is with respect to learning a good representation to solve these tasks. So it's all about representation learning, and I'm going to share basically a few examples. For perception, we have an image, and our goal is to, from the image, extract all these perception tasks. But because we are interested in a real-time solution and potentially computational effect, low-cost solutions with low memory usage, we do want to be able to develop neural network architecture that will do this jointly. Just with one network, we'll be able to extract everything that we need on the perception step. And when we were trying to look for a shared representation, we have to innovate on how we want to combine all these tasks together. How can we handle the gradient in an efficient way, coming from all these different tasks that have different data set, different number of examples, and how to be able to still learn a shared representation without losing performance by combining all these tasks together. So we have more details in one of our paper here, where we show that we can extract 32 attributes without necessarily losing a performance. And these are some examples of what we can extract. We can extract the appearance of the pedestrians, their behavior, but also their intention to potentially, for instance, cross the street or not in this case. Here are some illustrations, some visualization of predicting the intention to cross the street. So whenever it's in blue, we believe that the pedestrian will cross the street. We are also interested in extracting 70 key points on all the objects of interest, not only humans, but also vehicles, bicycles, animals, and so on, and do this all with a single network architecture. And then once we have all these 70 key points, we can also develop different type of neural network that, given skeletons, will actually do 3D reasoning, action, understanding as well. We show that we can locate objects, humans in this case, in 3D, given just a single camera that extract 2D skeleton from the image, and from the skeletons extract the depth of these objects. We can also understand like eye contact with this skeleton, but we can also extract scene graph on the potentially relationship between object and humans and the scene. And it was, in fact, this work was presented as WACV a few years ago. But then what is the current challenges in solving perception tasks is we still struggle to detect rare actions. All these class of objects that we don't necessarily have training data, or we have very limited examples. So it's very difficult to suppose that we can have training for all the possible objects and actions that we might observe in reality. So how can we address that? Now I'm going to talk about it later on. Then for our second pillar, the social forecasting, it's all about learning to predict. So we observe a sequence of trajectories, point in time, coordinate of objects, and we want to predict their next coordinate. And over the years, we have developed many neural network architecture to do that, where we studied also a new way to bring causal reasoning on the representation that we're learning to do this task, how to impose some low rank adaptations. So suppose that you're able to learn to, or you have enough data to learn to predict pedestrians, but you also want to predict a different type of agent, like a bicycle. Can we transfer, can we just fine tune or adapt what you have learned from pedestrians to this new class? And yes, you can by using similar ideas as LoRa or Clora, all these low rank adapters. And then also recently, we show that you can use diffusion model to learn the multimodal representation and have a promptable way to deal with this task, which means that you can use multiple type of modalities for input. It can be just coordinate, but also the skeleton of humans to better predict where they will go. But what's the main limitation of all this forecasting work is that when you do only fully data driven, your performance depends on the distribution of your training data, of whatever data you're collecting. And then you cannot necessarily guarantee that you're able to predict or learn the basics behavior or even the physics behind these dynamic. And we showed in some other work that even if you take state-of-the-art deep learning method that are ranked first in some of these forecasting challenge, they don't necessarily do a good job in predicting some very basic behaviors because they are out of the distribution of the training data. And I'm going to also share a few ideas on how to address this. And finally, on planning, it's very similar to prediction, but you do have access to the goal. You know where you want to go. And we also showed that
keynote EPFL
to improve the planning performance, if you can bring more labels and generate more synthetic data of wrong behavior, you can actually improve your policy. It's because you usually have actually data from good behaviors, of good interactions, of humans interacting with each other. But if we also supervise our training with some contrastive loss, with examples that are synthetic negative examples, it actually gives a boost to our performance. But yet, nevertheless, we are not very robust to distributional shift. We still struggle to potentially transfer what we have learned from one environment to another one. So these are all the current limitation of our modules. And the question is, how can we move forward and address these challenges? And I suggested 7 principles that we believe can help in moving the field forward in addressing these challenges. So let's look at the first 2, the principle of prediction and the principle of opposites. All these principles are towards what kind of guidelines or thinking can we do to improve the learning of a representation. So it's always in the context of, I want to learn a powerful representation. What kind of supervision, what kind of constraint should I impose on my learning scheme to better learn these these tasks. So the first principle is about arguing that a representation that learns to predict sensory input response or the signal itself is a powerful representation to learn other tasks. And this idea is not new. It goes back to 1860. Neuroscientists argue that our brain actively makes prediction about the world based on past experience. And this is what foundation models are about these days. Generative pre-trained transformer. They learn a representation to predict the next signal, the next token. It can be a text, it can be a word, it can be an image. And then they are fine-tuned with the principle of opposite. And the principle of opposite tells us that learning is successful by means of opposite through the contrast of positive and negative example. As Rumi said, things are known by their opposite light by way of darkness. So I believe that representation learning in general can be staged as two steps. First, let's learn to predict anything with unlimited labels, and then let's learn specific things with few examples. And then we can potentially detect rare examples and that rely on few examples. So we have started to do this a bit. So we have recently actually developed a foundation model that, given an image, predict the next frame, the next images. We can also look at it as image to video or a word foundation model. We have several input. It can be RGB, but also depth. And here we show that we can develop a method. We have developed actually a model that given an image and some actions on the control on the image, we can generate the next frames, the next the video that comes out of it. We actually developed this based on the stable diffusion architecture, where we show that we can bring some new controls to it. And we trained it with pseudo labels. So we collected a lot of videos from YouTube. I mean, we just used them, about 2,000 hours of video of cars driving around, and then we run algorithms to detect the depth, the skeletons, the objects, the ego trajectories, all with pseudo labels, and we train our image to video transformer to architecture to solve the generative task. And this is, we're not the only one doing that. There was this recent work from NVIDIA, Cosmos, sharing a foundation model. They have used a lot of data, 20 million hours of data, a lot of GPUs, and they have shared their model recently. So we are doing something a bit similar, but with much less data and resources, but with more controllability. And here we are showing you some qualitative result of what we are generating. Again, the input is just one frame, and then we generate the video that comes out of it. So this is an illustration. On the left, it's our input, and we learn to generate the next frames. And we can control, we can say, I want to go right, generate a video that will go right, and I want to go left and generate a video that will go left. There are some other examples. We can also have a control on the content of the image. We can say that I want this motorcycle to go from right to left. This is what we have shared on the left of the reference frame, and then it generates the video accordingly. The same for this car, or suggesting or asking to generate the dynamic of a car. or to move the cars around in our video. We can do the same with pedestrians. We can ask the model to generate when pedestrian will cross the street, how it will look like, or if they stay still. We are generating multi-modalities. So we are also, for instance, generating this depth jointly with the image. So this was the work that we did to develop this self-supervised learning, this foundation model. We also do this with vectorized input with trajectories only, where we're interested in fact learning a foundation model to predict, to generate trajectories. So we did a similar work where we try to unify all the existing data set in the context of autonomous driving, make a unified format, and then train and learn a foundation model with that. The third principle is the principle of multimodality. And again, it's also to motivate it to detect these rare actions. And the way we look at it, we believe that we can interpret the world through multiple senses, and this highlights the importance of leveraging additional source of information. And until recently, neural network architecture were quite different across modalities, such as vision, audio, and NLP. But nowadays, the same architecture, like a transformer network, can deal with all the modalities. So you can learn to align this latent representation between vision and language and benefit from the knowledge available in one of these modality, in this case, LLMs, for instance. And then you can use it to recognize or understand rare actions thanks to the knowledge that you have learned from text. And do zero-shot classification, for instance. And the fourth principle is the principle of residual learning. And this is motivated to address this challenge of not forgetting basic behaviors, or to be able to detect also predict basic behaviors. And the way we motivate it is, as I said, usually nowadays, state-of-the-art prediction method learn the task of prediction from scratch. They use the whole capacity of the network to learn everything about navigation or trajectory prediction. But we do want to use the data to only learn concepts that we struggle to explain, like social norms, for instance, but not necessarily things that we know, like the physics behind it, or like very common behaviors. Why do we don't necessarily need to learn them from data. And so what we're suggesting is to use our knowledge-driven methods or physics-based method as a starting point to solve the task, and augmented with data-driven methods. In other words, to correct the output of knowledge-driven methods with constrained residuals that are learned from the data to be able to update the behavior. And only focus on these potentially social norms. And we have shown that we can also do this with vehicle. We know that, for instance, the trajectory of vehicle needs to follow the road, cannot go off-road, has a bit of some physics behind the dynamics. So we use that and then just try to update these knowledge-driven method with our neural networks. The fifth principle is the principle of compositionality. And I like to revisit it as follows, like saying that the world that we see, the collected signals or the perceived concept might look complex at first, but they might be the composition of few simple concepts that you combine together. And the challenge is to find these few concepts, these atoms of a dictionary. For instance, the space of possible interactions and social interactions is large, but it's the composition of few atomic learnable concepts. And by learning them, we can adapt and maybe learn to be less impacted by shift in distribution. The sixth principle is the principle of causality. So our ultimate scientific goal in machine learning is to learn causation, the underlying cause effect. Yet the field of representation learning or learning correlation in the data. So we can study how to learn causal representation by injecting weak causal supervisions. For instance, we can potentially learn in simulation some causal relationship with counterfactual experiments, get this annotation and use this annotation to supervise our learning to better model the causality and transfer whatever we learn into the real world, and hope that this actually remains in the real world. And we have shown that, yes, this is possible in a recent work that will be presented in CEPR. The last principle is the principle of in vivo practice, which means that in vivo refers to systems that operate in contact to humans, as opposed to in labs. And what we know is that human behavior change in space, across cities, in time, over the years. So it's unrealistic to suppose that whatever we have learned will remain, and that distributional shift will not occur. So can we adapt our representation on the fly? So can we develop method that at test time adapt to the dynamics? And what kind of auxiliary self-supervised task we can impose to learn these shift and update our representation on the fly? And there's this field called test time adaptation that is actually studying that. And I think that this is also a very good area, and we should consider it when we develop our system. Voila, all these principles will impact the embedded AI of all our autonomous mobility applications. I want to, so I've talked about like self-driving car, autonomous robot. Let me share maybe one last use case that I think it's super fun. It's on human body. So we use this to help paralyzed human to move again. Humans paralyzed with spinal cord injury. And the way we do that, we use our robot to detect the skeleton of the patient, predict what the patient should do to walk. I mean, what should be the ideal skeleton, and control the electrical stimulation of their muscles to match the ideal behavior. And this is a demo. Our robot on the left is looking at the patient and controlling the stimulation to his muscle to make the patient move in a way that we believe the patient should move, thanks to our prediction module. So I'm going to end here. To sum up, we have all these principles that we want to apply to our 3 pillars and demonstrate their use case across applications. And let me finish with this video. Suppose you have this autonomous vehicle that detects the pedal and the pedestrian. What should the AV do? Well, avoid the pedal. Shall we make it a hard rule and always avoid a puddle? Well, in some context, the autonomous vehicle should read the humans to splash them. So it's all about AI reading humans. Voila. Thank you. If you have any questions.
Thank you, Lauren. Are there any questions from the audience, either Zoom or in person? Yes. If it's a long question, you can also come here, maybe. You can also try this, but I'm not sure if they're gonna hear it. Maybe. Yeah, to see also.
Yeah. Well, first of all, congratulations for such a powerful publication. It's indeed impressive list. My question was about the last principle, the in vivo practice. How is it similar and how is it different from reinforcement learning?
How is it similar or different from what?
From reinforcement learning.
From reinforcement learning?
Yes.
Yes, so the way it is a bit different is in reinforcement learning. Yes, so you have learned a policy maybe in simulation, or you do have a working policy that will take action in the environment, and even if the environment change a bit. But what if the behavior of your agent has changed and it was not actually in your simulator, or you or in whatever data that you had that you try to learn your policies? So the question is, for instance, we have pedestrians that are walking in a specific way. We are simulating that and we're learning good policies to interact with them, but they change their behavior in a way that we did not imagine before. For some reasons, they go faster because of evolution, or they decide to change some rules in navigation, and they do it. How can we, and what can we do with our existing method? How can we adapt them on the fly to react to this change in behavior? So we need to have a mechanism that potentially look at the data on the fly, maybe update its parameters, the model that it has, to handle this shift in distribution. So this is my way to look at it.
Thank you. There's one question in Zoom from Arnold. He asked, would you think reasoning capabilities shown recently in the LLM space are useful for the 7 pillars? Where would you think it would fit well?
I think it's useful for the multimodality pillar. Yes, in fact, here, if we are able to align the representation of an image or a video with some sentences, then if we see something that we're not used to, we can take advantage of how a LLM, the knowledge that exists in a LLM, the reasoning that maybe exists in a LLM to tell us what will happen. For instance, if we see the image of a ball in front of a street, and maybe a kid, or we know that there is a school nearby, and we ask the LLM what will happen, the LLM will tell us there is a chance that a kid will come pick up the ball because there is a street, there is a school, and so on. So there's a bit of a knowledge in the LLM that will help us better predict the future, although we never actually had this in our training data. Does it make sense?
For me, it makes sense. Arnold has answered, but yes, he also agrees. Is there any more question? Otherwise, I have one final question. So my question is about, I'm working with the startup Lookout, and we want to propose paths for boats. And this path depends fundamentally on the paths of other boats. Like, how do other boats essentially drive? How do they behave? And unlike in the autonomous driving scene, where you have very rigid rules, obviously they're broken also sometimes, but you don't have the concept of lanes, for example, in boats. So it's really hard to predict kind of where another boat is going, and depending on that, where you're supposed to go. And so my question kind of would be, what's your take on, have we solved, let's say, vision enough? Like, is the vision that we currently have, the 3D construction, is that good enough to predict such subtle things like social forecasting? Like for pedestrians, I imagine faces can be really small in image space and pretty far away, and you can barely see whether this person kind of looked at you, whether that person is aware of you. Do you think sensor-wise, vision-wise, we're good enough already to do these things, or do we have to do a better job on that? Yeah, that makes sense.
My safe answer: we're not good enough, so it's easy. So we still have work to do. Otherwise, we're jobless. But then, yes, I think in your own domain, it's a very interesting domain. The causality behind predicting the behavior of other boats, for instance, depends also on the nature of the climate of other data, or the sea that you need to potentially model. But we are showing that we have the methodology to do that. So in our methodology, in a self-driving car, we also use the scene, but it's a bit static. But for humans, we have other cues that are more dynamic. So we have the architecture to handle multiple modalities, multiple input to learn to predict, as long as we have enough examples. And if we don't have enough example, can we learn from other agents and transfer potentially thanks to a foundation model on prediction? And I think this is where we are going. We're trying to develop a foundation model on prediction, so that, for instance, this one, so that we can, in fact, in other domains, rely on less example, but still do a good job in predicting.
Yeah, that makes sense. Perfect. Yeah. Yeah, I found it really inspirational, especially also like your part about like where you source 2,000 hours of YouTube video. So as part of this company I'm working with, I also learned YouTube is just a source of so many data. So in the marine domain, we oftentimes like complain about few data sets compared to the autonomous driving domain, but there's actually a lot of out there. It's just maybe not as structured yet, and can be sourced. Okay, cool. Thanks, Alex, for a very nice talk. And yeah, hope to see you soon again. And
yes,
then, thank you.
Enjoy the workshop. Thank you.